Great. All right, good morning, afternoon, or evening, everybody. This is your host, Jennifer Brennan. I'd like to welcome you to the Big Things Come in Very Small Packages, SeaHawk, a new way of looking at the ocean, Earth Data webinar. It is 2 p.m. Eastern Time, so we're going to go ahead and get started here. And what I'd like to do first is begin with just a few webinar logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you'll see that located on the right side of your screen. Today's webinar is being recorded. The recording will be posted to the NASA Earth Data website, as well as to our NASA Earth Data YouTube channel within a week of completion. And what I will do a bit later is post those links within the chat for all of you. But I will follow up with a thank you email, and that will include not only a link to the recording, but also a link to the presentation slide deck from today. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and demonstration and an additional 15 minutes for the question and answer period. During today's webinar, we will have one speaker, and we also have 2 Q&A panelists. Our speaker today is Sean Bailey. He is the manager at NASA's Ocean Biology Distributed Active Archive Center, or OBDAC. We also have the 2 panelists, which will be present during the Q&A at the end. Our first panelist is Alicia Scott. She is a member of the SeaHawk HawkEye operations team, also at the OBDAC, and Dr. Sarah Rivero Calle, who is the science lead for the SeaHawk HawkEye mission, and also an assistant professor at the University of Georgia Skidaway Institute of Oceanography. So what I'd like to do now is just pull up today's agenda here. Just give me just 1 second. Hopefully you can see that okay. Our speaker will begin today's presentation with an introduction to the Ocean Biology Processing Group, the OBDAC, and also ocean color observations. And then from there, he will introduce the SeaHawk HawkEye CubeSat mission and transition to a discussion of the HawkEye sensor characteristics and calibration information. And then finally, what we'll do is we'll wrap up today's webinar with a live demonstration that will show you how to access and visualize HawkEye data using the CDAS software suite. Once our speaker has finished with his presentation and demonstration, we will transition to an optional final set of polling questions. And I will give these questions, at least within the webinar, approximately 5 minutes or so before transitioning to the Q&A session. But the questions will be open much longer than that for those of you who would like to provide feedback. So from there, we'll move to the Q&A period. Depending upon the volume of questions that we receive this afternoon, we'll extend the Q&A period an additional 15 minutes from end time for those of you who wish to stay in the line, but we will have a hard cutoff of 3:15 p.m. And just a quick note about the Q&A period. We'll try to answer as many questions as we can within the time allotted, but if for some reason we're not able to answer your question or address your query during Q&A, our speakers will follow up with you offline. With that, it is my pleasure to introduce today's speaker, Sean Bailey. Sean, I'm going to stop sharing and toss the presenter role over to you. Just give me just 1 moment here. All righty. All right, Sean, you should have that.
Thank you, Jennifer.
All right, perfect. I do see your slides.
All right. Well, once again, welcome everyone. As Jennifer mentioned, I'll be talking to you about a topic called Big Things Come in Small Packages. Let's talk about an instrument called HawkEye flying on a CubeSat called SeaHawk. But before I do that, to give you a little bit of a background about who we are at the Ocean Biology DAC and our sister project, the Ocean Biology Processing Group. The OBDAC and OBPG consists of a number of things, a number of elements. One of the first and primary is we are a data processing system. When we can have a database-controlled distributed processing system for the production of ocean science products, ocean color and SST from a number of missions. We also provide a software repository we call the OCSSW, which is made available to our users through the CDAS package, which allows us to have configuration control of our science processing software and gives us a common software suite for being able to process these multiple missions from observed radiances to derived products. We also have a validation system. Ocean Color is a complicated little beast to wrap our hands around, and in order to ensure that we're producing credible products for the community, we must validate those data. So we have data processing and quality control of Ocean Color field data, coupled with an automated matchup system for the statistical assessment of these derived products. And that is through our in situ archive called CBAS. We also make use of some data produced at a sister Goddard entity called AeroNet, which has some automated robot radiometers, ground-based radiometers that measure, a few of them actually measure radiances coming from the water, and we use those as well. And then we are an archive of these data. We have a multi-petabyte archive that allows us to store and distribute satellite radiances and derived products from a number of missions, including the list over here on the panel in the right. A number of these missions are global in that they collect near global or global coverage every day or two. Those include missions such as VIIRS, MODIS, CWIFS, CZCS, some international partner missions we have as well, MERIS, OCTS, and the Sentinel-3 Ulchi sensors as well. A few of those missions are only regional in collection, and so those would include the GOSI instrument, which is from the Korean Space Agency, and that is a geostationary instrument that looks primarily at a region focused on Korea and Japan Sea. The HYCO instrument, which was on board the International Space Station, and the instrument I'll be talking to you about today, SeaHawk. In addition to that, through our CDAS application, we provide support for a number of missions that we do not archive or distribute to make it possible for users to be able to process those data as ocean color, if they're ocean color capable, such as the Landsat instrument on Landsat, the OLI instrument on Landsat 8, the MSI instrument on the Sentinel-2 platforms, OSMI, OCM from India and Korea, an old instrument called MOS from Germany, and a recent launch from Japan, replacement of OCTS and called SGLI. In the future, we will also be providing to you data from the PACE mission. But today, I'm going to speak to you about a project called Sustained Ocean Color Observations from Nanosatellites. That project is depicted here. We have the SeaHawk CubeSat flying over the Earth in a representation. I think this is a pretty cool picture myself. All right, but how do we get to SeaHawk today? Ocean color instruments from space began in 1978 with the launch of the CZCS instrument on the Nimbus 7 platform. And following on that, the first, what we call modern ocean color instrument was CWIFS, which was launched in 1997. And it's the reason I'm here. I began work with the CWIFS instrument back in 1997. In 1999, the Terra instrument the Terra platform was launched with the MODIS instrument on board. As you can see, we're getting a little bit bigger here. We went from CWIFS at about 309 kilograms and maybe 2 meters in length to the platform of Terra, which is pushing 6 or 7 meters in length and over 4,000, almost 5,000 kilograms. Europe decided to beat us and best us with that, and in 2002 they launched ENVISAT. And I think ENVISAT takes the cake for being what we call a satellite bus, because it is literally the size of a school bus in space. It's approximately, well, over 10 meters, maybe almost 11 meters in length, and nearly double the mass of the Terra platform. Now, to be fair, both Terra and EnviSat included more than a single instrument, whereas CWIS was just a single instrument platform. But as you can see, things were getting bigger as time went on. Recently, a little more recently, we had the launch of the JPSS-1 or NOAA-20 spacecraft, which, as the other predecessors, has multiple instruments. One of those is the VIIRS instrument. We've come down a little bit in size. But now we have SeaHawk. Unlike its brethren flying on these much larger platforms, the SeaHawk instrument is all of about 4 kilograms in mass. And as you can see, it's much, much smaller than the others. It provides us some unique capabilities, being able to have a smaller instrument on a CubeSat. It's much cheaper and can be produced much faster. And well, how much smaller is it? And what is small? Well, we refer to the SeaHawk instrument or platform as a 3U CubeSat. What does U mean? U is short for unit. We're clever people. 1 unit is about 10 cubic centimeters, so 10 centimeters by 10 centimeters by 10 centimeters on the side. 4 inches or so for those of you who speak English units. How does that look? Well, on this image here on the right, you can see that there's a mock-up of the size of the HawkEye instrument. The 8 ovals in the top of that top panel there are for the 8 bands that are on the instrument itself. To the right, I've kind of obscured the beverage can, just so I wouldn't promote one or another. But you can see it's about this, the height of a standard can of soda. You can hold this instrument in your hand. So, an idea was born. Can we construct and launch a high-resolution, approximately 120-meter resolution, proof-of-concept ocean color instrument that's capable of being carried on a 3U CubeSat platform? All right, got an idea? Now we need a plan. How are we going to make this happen? The SeaHawk mission was conceived. In about 2015, a proposal was made to the Gordon and Betty Moore Foundation, and they were impressed and decided to fund this program. So now that we have some money, we have to start designing and constructing. So in phase 1, we had to find a partner. We needed to find a CubeSat provider, and the one that was selected was Clyde Space, which is based in Scotland, and they provided 2 platforms, the SeaHawk 1 and SeaHawk 2. Cloudland Instruments, based in California, was brought online to provide the HawkEye sensor. The president of Cloudland Instruments, Alan Holmes, was the man responsible for the development of the CWIS instrument. So we have some heritage here. Dr. John Morrison of the University of North Carolina, Wilmington, was brought on to administer this program. We at NASA here were brought on to advise and to review during the development phase of the program. And ultimately, a formal NASA Headquarters Space Act agreement in 2017 was signed, which authorized us to provide support for the collection, processing, calibration, validation, archive, and distribution of these data. And then we have to launch it. So the funding we received from the Gordon and Betty Moore Foundation in 2015 provided for the first part. Once we demonstrated we had an instrument and we had a spacecraft that it could fly upon, we were given an additional grant in 2017 to support the commercial launch and operations of this platform. Some key mission parameters. The SeaHawk instrument was launched in December 3rd, 2018, along with, I think it was 62 of its brethren little CubeSats. They all launched together off of a SpaceX launch. We were launched into an orbit of 585 kilometers, sun synchronous, so at approximately 10:30 a.m. Equatorial crossing time, which is roughly the same as the Terra platform. We have about a 19-day repeat orbit, so every 19 days we go over the same spot on the Earth. We expected a baseline orbital lifetime for being about a year. We're hoping 18 to 24 months. The image that we get from the SeaHawk sensor is approximately 200 by 700 kilometers in size, with a resolution of roughly 120 meters. Each one of these level 1 scenes that we get is approximately 180 megabytes in size. We're capable of storing 18 of those images on board, which means that if we were to want to collect any more data, we have to download those data. 180 megabyte scenes is quite a little beefy for this little spacecraft to be able to pump it down using S-band data, which is typical, or UHF data, which is typical for many CubeSats. So SeaHawk has a unique capability in that we have an X-band transmitter on board, and which allows us to have data rates much greater than any other CubeSat. We can download up to 100 megabits per second, which was necessary for us to be able to collect these data and download them efficiently. The instrument itself, the HawkEye instrument, weighs less than a kilogram. The total weight of the spacecraft and the instrument is less than 5 kilograms. SeaHawk, or the HawkEye instrument, was based off of off-the-shelf CCD arrays. In fact, very similar to the arrays that are found in common colored copiers.
Sean, my apologies for the interruption. If you could speak up just a little bit, I think that would be very helpful. Thank you so much.
Sure.
Thanks for your patience, everybody.
This is not the first time I've been chastised for speaking softly. The HawkEye instrument has 8 bands that are similar to the SeaWIF's band set, and it's open intellectual property and encouraging knowledge sharing. So, it is a fully qualified spacecraft. Ocean mission, it produces, or it downloads the data through the X-band processing to receivers at Wallops Island in Virginia and in Alaska at the Alaska Satellite Facility. The Applied Space Mission Operations Team uploads data to the spacecraft from their location in Scotland. And NASA's Near Earth Ground Network collects those data and distributes them to us at Goddard. We work with the folks at the University of North Carolina at Wilmington for the science operations. We communicate with the Cloudland folks for continued calibration and characterization support of this instrument. We treat it as many of our other instruments. We have a science team. We have the CBAS validation data that we collect for it, and we have you, the science community. So it's everything that we would do for any other one of those larger missions we are doing for this tiny little CubeSat. What is our current status? Well, we've been on orbit for over 3 years. Now, if you recall earlier, I said that our hope was to have a year, maybe 2 on orbit. But we have been successfully flying around for over 3, which is great. It was in June of the last year that we finally transitioned from into routine operations, which was quite a bit of a longish time, but there's a reason for that. I'll get to it in a minute. Since that time, since we launched, made our first image on March 20th of 2019, we have collected over 2,600 images. Every day we get downlink, X-band downlinks at either Wallop Island or Alaska, and we have weekly image scheduling to allow us to collect more data or schedule more image collection. And the data that are downlinked are automatically processed to level 2 and made available on our distribution website. For our routine operations, SeaHawk has a unique offering in that we allow community requests for image capture through the University of North Carolina website listed below here. So you, as a researcher out in the field, can decide if you would like, you can make a request to have SeaHawk image over your region of interest. If you go to the University of North Carolina website, you can drill down to the image request page, and you can click on the request pay form here and make your request for certain periods of time. The instrument, because we schedule these weekly, there's a period of time when requests are accepted for a particular time in the future. For our weekly ground station downlink image uplink and scheduling, each week the science operations team communicates with the Near Earth network to request downlinks at the Wallops Island and Alaska ground stations. The confirmed downlinks are combined with these image requests, both those made by the community and those made by the science team. The best uplink opportunities are then identified and inserted, and once completed, this plan gets sent to the Mission Operations Center in Scotland, where it is uplinked to the satellite for collection. We also have a Science Operations Center here at NASA Goddard, where we provide linked from our website here at the Ocean Color website, oceancolor.gsscnasa.gov/SeaHawk, provides you a dashboard. From this, you can see keep track of our daily operations here at the Science Operations Center. You can see how we command the spacecraft. When you arrive at this link, you'll see the SeaHawk dashboard, which shows the mission operation status. In this case, the normal operating status is called mission mode. There are controls underneath this that allow you to choose what date you would like to view the information for. The first tool below is a globe that displays where the SeaHawk's location is at any given point in time in relation to the Earth. Next, you can see a map of the displayed areas that are planned for capture, that have been planned for capture by the team. A timeline is used if one prefers to watch for when the spacecraft will pass over a ground station and what capabilities that ground station would handle at that time. After the ground station pass, the science operations team provides the image data and publishes it to our image archive. And finally, users can see the status of all these commands that have been submitted to the science operations team by the science operations team to the Mission Operations Center at Clyde Space. Because SeaHawk is a tiny little beast, and we're trying to measure at 120 meter resolution on the Earth, its navigation isn't perfect right off the bat. So some manual adjustments are necessary for a number of the scenes. So we have a tool that allows us to display the captured image overlaid with ground control points, and we're able to adjust the image until the geolocation, the patterns match up, which allows us to then reprocess the navigation information to provide better geolocation for the individual scenes. SeaHawk is special in that because we can target, we have the ability to roll the spacecraft during orbit so that we can collect simultaneous measurements over the same spot on the Earth over consecutive days. I believe we have demonstrated up to 5 and believe we can actually get to 7 consecutive day coverage over a single spot on the Earth, which is pretty spectacular if you consider that most of those polar orbiting satellites that we have, the big behemoth guys, can only see the same spot at most, maybe twice, if you're lucky, depending on the orbit. But because we can point our little spacecraft, we can actually see more. And here's a series of data that were collected in November of last year over Northern Australia. And you can see that we did pretty good. Because we're pointing this instrument, these images were collected at nadir view. Typically, the spacecraft, when we make its collections, we are tilted, as we did with the CWIS instrument, by about 20 degrees fore or aft, depending on where we are relative to the subsolar point to minimize glint. When we were doing this test operations, we were nadir pointing, and so as you can see, as we pointed into the glint, we saw a glint. Fortunately, we've been demonstrated that we can do this with the tilt as well, so that should be able to mitigate glint problems that you might find. This is great. But if it was launched in 2018, why does our data availability begin in 2021? That's a good question. It was a little difficult getting this spacecraft stable. When it was first launched, the attitude control system was not refined as it could have been. As you can see, as demonstrated by some of these earlier images, they're very pretty, very artistic. We can actually see the limb of the Earth, we'll see some space. But this isn't very useful if you actually wanted to make scientific use of these data. After a long commissioning phase and lots of going back and forth with the Clyde Space folks on spacecraft, we were able to get the navigation and the control of this beast much, much better. And we are now able to happily provide stable data to the public. All right, well, if you get that data, you might see some things that are funny. In this case, I'm showing there's some lines in the sea. There's some lines in the data. And what's all that about? Well, as I mentioned, the instrument is commercial off-the-shelf CCD arrays. Because it was built quickly and it's small, there isn't basically we don't have much of a windshield. And sometimes dust particles will fall onto the sensors. And if a dust or particle falls over, obscures one of the pixels in that CCD array, it will be translated into a line that shows up in the data. As you can see here, this image on the right shows the pixel number and its relative response. So for a flat field for the sensor. And as you can see, there's this little spot over here where there's this big dip, and that is what we believe to be a dust particle that has impacted the sensor. When we identify these, we are able to then provide an updated flat field calibration table and remove that stripe and make it reasonable data again. But it takes time. But that's not all. Isn't calibration fun? We have identified what is possible, a possible response versus scan problem with the instrument. Response versus scan is a little funny in that we're not scanning, we're actually a push broom, but what this is saying is that there's a non-uniform response across the detectors that we may have to sort out. As you can see, it demonstrates in this particular scene as what appears to be a brightening of the data at the edges. We have some ideas on how to correct this, and we will be working on a revised calibration, hopefully getting that out to you shortly. Oh, but there's more. There are what we would like to, well, afraid we have to have some ghosts in our machine. You can see this image here. There's an island in the middle of the scene, and there appears to be a duplicate of that island a little bit to the north and east of its location. The good news is that's not in all of the bands. So we haven't all lost, all hope is not lost. So in this particular case, what we're looking at here on the left is data from the 867 nanometer band, which is the longest wavelength band that we have, which was planned to be used for the atmospheric correction as we do with all of our other ocean color instruments. The panel on the right shows the data from the 670 nanometer channel, which does not have that ghosting problem. So as a result, we have chosen to use a atmospheric correction approach that was similar to what was done for the CZCS instrument. The prototype instrument that was launched in 1978 did not have the near IR bands that we had with CWIFs, and we were able to have a successful atmospheric correction approach. With this, it's a little bit limited. It would be better if we could trust the near IR bands, but since we can't, all of the data that we process now are using the 670 nanometer band for the atmospheric correction. But given all of that, it's not too shabby. Now, our current processing is actually surprisingly good. On the left-hand side here on the panel, you see an image that was collected from the MODIS Terra spacecraft in June of 2021, near the Mobi site near Lanai, Hawaii. That red circle there, if you look underneath that, the chlorophyll at that point is roughly 0.72 milligrams per meter cubed. The right-hand panel is the same scene imaged by SeaHawk on the same day. And as you can see, at the Mobi location, we nailed it. The CWIS instrument, the SeaHawk platform, the HawkEye instrument, measured the same derived chlorophyll value as that we were getting from the MODIS Terra instrument. In addition, because we have 120 meter resolution, this image here showing on the top the HawkEye measurements of around the Bermuda Island in the Atlantic are much sharper, much finer detail in the eddies coming off of around the island than you can see in the MODIS Terra image below. So we have credible data. It matches what we're getting from the big boys in space, and it does it at a higher resolution. Well, what does the future hold for us? The spacecraft has lost only about 1 kilometer of altitude since it was launched, which means that it's likely to be in orbit for much longer than we expected, which is good because it took us much longer than expected to get it stable enough to be able to give us good data. There are no end of missions trend being observed in the spacecraft systems. We have had a few safe hold events where the instrument went offline for one reason or another, but we have been successful in recovering from each and every one of those. The most recent one of those was earlier in December, but we recovered from that and have been collecting data successfully since January 10th of this year. We have a request in the works to the Moore Foundation to provide an additional 3 years of operational support, and the Space Act agreement that we initially signed in 2017 is set to expire, and we're looking to extend that beyond its expiration date of June 2022. All right, now, how do you access and work with this data? All of the data, all of our ocean color data, HawkEye included, are available from our ocean color website. And this here is a panel on the left shows an image of our level 1 and level 2 browser on which you can browse for these data. Once you have the data, you can visualize them with a software package that we call CDAS that we also make available to the public. It's free and easy to install on all platforms. It works on Windows, Macintosh, and Linux systems. And now for the scary part, a live demo. Here we go. I'm going to switch modes out of presentation and show you our website. So if you go to our Ocean Color website page today, you will be presented with this site. If you wanted information about the HawkEye instrument under missions here, if you click on the HawkEye page, you'll get a summary of information about the satellite, some links to important information, including data access, and as well links to the project page hosted by the University of North Carolina, Wilmington. But we're here to collect some data. So if you go under data, you click on our level 1, level 2 browser, the same link is available here. We can get directly to it through this link here. It will be brought to the level 1, level 2 browser. It's already been selected for the HawkEye instrument. As you can see, the data that have been collected for the whole mission show up in this panel above. I'm kind of partial to that November scene where we collected a series of data over Northern Australia, so we're going to drill down to that. In this panel below, we can select the month of November of 2021, and then we're presented with a 3 months view of time here, and we know that that image was collected on November 11th, the first one, so we'll click on that date, and as you can see, the image above has changed, so now we are presented with just the data that have been collected on that day. If we were to then click on the map here at this scene, we'll be presented with a browse image of the data, both in true color form and a chlorophyll image. We like that data, so we can go ahead and download it. These links above allow you to immediately have access to this data. So if you were to click, you're brought to the Earth Data Login webpage. All of our data are required to have for the user to have an Earth Data Login account to download. It's a free account, free to register. So if you don't already have one, you can click here to register. I happen to have one, so we'll go ahead and put my credentials in here and we will log in. This page here is redirecting us back to our page. If you notice, we started to download that scene here, but we're still redirecting, which is a little disturbing, you might find, but there is a quick solution. We haven't quite figured out why this redirect happens, but it seems to only happen the first time you do this. If you click back, you can get back to the page, and then any subsequent downloads that you might want, since you've already logged in, will just download immediately without going and having that redirect problem. We're still trying to sort out why that is. It may be because this browser that we're working on was originally developed in the late 1990s and is still going, and maybe there's some age problem going on. We don't know, but hopefully we'll sort it out soon. With that said, we now have downloaded the data. Well, now what are we going to do? How are we going to look at that data? As I said, we have a tool called CDAS. If you go to our Ocean Color webpage, go back to the original page, you can see at the bottom of this page is a link to the CDAS program. So if you do not already have CDAS installed, you can click on this. It'll bring you to the CDAS webpage where you can download a copy for yourself. I already have it installed, so let's go ahead and launch that and see where we're going. Now, since I've already downloaded these data, we can go ahead and open them up. If you click on the little file icon here, it'll bring up a browser. I'm already in the directory for which I've downloaded the data to. This is the scene that we were playing with. If we go ahead and open that, CDAS will load this. In the File Manager panel over here, there's a little cookie unwind here. If you unwind this, you'll be presented with a number of things. The data are under bands. We have them organized here by remote sensing reflectances, diffuse attenuation coefficient, aerosol optical thickness, and some other derived products. Angstrom product B, chlorophyll, which is the one we're going to look at right now. So if we double click that, it brings up the chlorophyll image. As you can see, that's the same scene that was available, presented to us on the browser, is now available to us here. What's nice about this is that we can, if we look over here on the pixel information, as we zoom, roll our cursor around over it, we can get a representation of the values of chlorophyll under our pixel, under our cursor. We can zoom in, if you like. You can see all these nice features. If we're curious as to knowing why there's missing data, we can go to the mask manager, and there are a number of level 2 flags that are applied by our standard atmospheric correction code to all these data as it's processed. One of those is land, so if we click on the, that's right. As a caveat, because of the navigation issue, the land flag is actually turned off. So we don't want to mask data accidentally. Forgot about that. This is the problem of doing things live. Clouds and stray light, they're actually white, so they turn up white, so you don't see that. Stray light is effectively just a dilation around the cloud mask. If you click on that, you can see we've masked out some data that may be affected by contamination from the cloud. So you can see a number of the other flags that are available to you here if you would like to click on them. Moderate glint. So remember how I mentioned in the scene that there's some glint contamination in the later days as we pointed into the sun. This scene, even though there isn't any obvious glint, it is affected by some moderate glint. So the atmospheric correction is capable of removing some of this glint, so it's still available and presented to you. If it were high glint, you could also click on that, and those data could be masked out. This scene doesn't have any, so we're lucky. Well, if you wanted to see where you are, the CDAS also has the ability to overlay a graticule map, so you can see where you are geographically. There's a world map, which shows you the scenes here over Australia. You can zoom in on that a bit. You can see where we are. This is how this scene was collected. CDAS is a rather complicated program, but is fairly intuitive. But if you do run into issues or questions about how it can be used or how you can use it better, we do offer comprehensive user support through the online forum. So we're going to go back to the web page. I'll show you how to access the forum. So if you have any questions, under support under CDAS, we have a number of help pages that are available for you. For the application itself. If you have any issues or would like to report it, you can go to the Earth Data Forum, where if you click on this, you're brought to the Earth Data Forum. This forum uses the same login credentials that you would need in order to download data from us. So if you've already logged in to collect or download data, you already have the ability to post on this forum to ask any questions of our staff. And I believe that ends my demonstration. Jennifer, if you would like to take control back.
Okay, thank you, Sean. At this point, we will open up our final optional polling questions and give those about 5 minutes or so. I've got a combination of multiple choice, multiple answer, and short answer. Although we'll give these 5 minutes right now, they will be open considerably longer if you're interested in providing input. So we'll give these 5 minutes and then we'll transition to the Q&A period. All right, so thank you, everybody. Let's give these just a few minutes here. And just a quick point, there have been a couple of questions that have been asked within the chat rather than the Q&A, and I will also try to capture those during our Q&A session. So thank you so much for all of the great input here. And for those of you who are wondering why you're not hearing audio, nobody is actually speaking at the time. We're going to give these optional final polling questions just a few more minutes, and then we will transition to the Q&A. And so that's why you're not hearing anything. All right. Thanks, everybody. Okay, everybody, at this point, we are going to dive right into the Q&A. And what I would like to do is actually ask those questions that were posed within the chat first, and then we'll transition over to the questions that were asked within the Q&A panel. So the first question here is, I don't know if I missed it. Could you tell us at what height the SeaHawk is orbiting?
Sure, it's orbiting at 585 kilometers.
Okay, wonderful. Thank you so much, Sean. And then if you could give me a moment, there was a question just maybe I asked. Okay. So the question was whether or not, if you could repeat whether or not CDOS works for Windows machines.
It does. The visualization package for the CDOS consists of two parts. There's the visualization tool and the data processing tool. The data processing tool includes the code that we actually run operationally in our production environment at the ODPS. That code is made available through CDAS and can be processed, so individuals can process the data locally, just as we would. However, because those codes are written for a Linux machine, they do not run natively under Windows. There are options for Windows users to be able to take advantage of those, including the Windows subsystem for Linux application that when Microsoft provides. With that, you can have access to the full power that you would have under Mac or a Linux system as well. There's just a little bit extra step that's involved to do that under Windows, but yes, it does work for Windows.
Okay, well, thank you very much, Sean. And our next question is, can you repeat what kind of hyperspectral camera you use?
HawkEye instrument is not hyperspectral, it's multispectral. It includes the same 8 or similar band set to the 8 wavelengths that were on the CWIS instrument. It is comprised of 4 commercial CCD arrays that were similar to those used in a common color copier. So it's not hyperspectral, but it is multispectral. There are filter sets in front of each one of those 8 windows that I showed you on that mock-up of the instrument.
Yeah, thank you, Sean. And I do see that Dr. Kaye had also provided a response within the Q&A. Our next question is, are these types of problems with sensor response unusual compared to all the other sensors you have worked with?
No, sadly. The CZCS instrument, in fact, that ghosting problem that I was mentioning, CZCS also suffered from that. They called it ringing. There are a number of response versus scan issues with the MODIS instruments. These are challenges that we have to deal with just about every ocean color instrument that we support. These particular ones, while specifically are unique to HawkEye, the problems in general of calibration issues are not. So.
Okay, thanks so much, Sean. And then I also wanted to note that one of our panelists who is new to the SeaHawk HawkEye team has also placed a link into the Q&A, which provides some very detailed information about the sensor specifications. And so hopefully everybody can see that. And what I'll do is I will put that into the chat for everybody just another time. And then let's move on to our next question here. Give me just one moment. I have added the link. Okay. Okay, the next question is, I don't understand the ghosting problem. It would be great if Sean could go into a little bit more detail as to why some land is ghosted while others do not appear to be.
That's a great question. The going in guess as to what's going on is that the filter set is actually delaminating a bit, and it is occurring on the longer wavelength bands filters and not on the shorter ones. And so that slight delamination is causing light to be scattered along the filter and hit the CCD array at a place not where it was collected. So that's our best guess as to what is causing that ghosting. So there's not much that we can do to correct for that. So right now the solution is to avoid it.
Okay, well, thank you for that, Sean. And then our next question is it fair to compare an instrument built in the 1990s with one built in 2017, 25 years later?
Fair? Well, it depends. A lot more money was spent in on the instruments that were built in 1999 than was spent on this instrument, even if you were to account for the change in inflation, significantly more money. So what we've demonstrated here with SeaHawk and HawkEye is that for much less in terms of financial outlay, you can get nearly as good, and in some cases better, data products. So
Well, that response provides an excellent segue to one of the next questions, which is, what is the cost of one of these CubeSats?
I believe that the cost for the initial instrument and CubeSat bus was under $1 million.
Okay, thank you, Sean. And then if you could repeat, what is the spatial resolution of the image at sea level?
That's roughly 120 meters.
Okay, thank you. Let's see here. I'm just moving down to, I see that there were some answers provided in the Q&A as well. Okay. The next question is, excuse me, at what point in the solar cycle was it launched? To lose only 1 kilometer of altitude means that it must have been on a low cycle.
I don't know the answer. It's quite nice that it's only lost a kilometer, but I do not have any clue as to why.
Okay, and so if Dr. Kayas would like to answer that, excuse me, that Kaye, that would be great. You should be able to unmute yourself.
Sorry, I just missed the question.
Yeah, that's okay, not a problem. And so, let's see here, give me just a second here. And I have lost where the question is here. Hold on a second. Okay, excuse me. At what point in the solar cycle was it launched? To lose only 1 kilometer of altitude means that it must have been on a low cycle.
Right, yeah, you're asking a biologist about that. I really don't have the answer to that. I can ask the engineers about it. I'm so sorry. Yeah, I was wondering about that question.
That's not a problem. So I think what we can do in this case is follow up offline with this particular participant. So thank you so much for your response. I appreciate it. And some of the questions have actually been answered within the Q&A. So let's move along to one that has not been answered already. Let's see here. Give me just one moment. Can you talk about the lens or the fore optics on SeaHawk?
Not with any confidence. There is some detailed information on the Cloudland website about the HawkEye instrument that does include this information, and if I can dig it up, I'll try and post it into the chat.
And I do think that the link that has been posted as well, that Phil has provided, should hopefully help to answer that question with the detailed sensor information. And if not, we can certainly follow up offline. All right, let's see here what else we've got going on. Are there any plans for follow-on missions or a constellation building on the lessons learned from SeaHawk 1?
And my cat distracted me and I missed that question. Could you repeat
That's
that?
okay. I'd be happy to. Are there any plans for follow-on missions or a constellation building on the lessons learned from SeaHawk 1?
Not currently. 2 instruments were originally commissioned and built, but because of the extended commissioning phase that we had and the issues we had with SeaHawk 1. SeaHawk 2 was not launched. We used the money that was going to be used for that launch to get the first one going. I do not believe that there are any current plans to actually build more and launch them, though. Well, it would be great.
Okay,
If
well,
I may add something to that, we're not in the process of launching anymore. We feel that there's been a lot of lessons learned from this mission, and this was a proof of concept kind of mission. If there's anybody in the audience who would like to fund the constellation, we would be happy to talk to you. But at the moment, we just wanted to prove that it could be done. And we're in the process now of analyzing the imagery. There's a follow-up proposal on the table right now for the Moore Foundation for us to continue analyzing the data for another 3 years.
Okay, thank you, Dr. Kaye. The next question is, let me just scroll down a little bit here. Is SST generated as a product?
No, HawkEye only includes visible bands. There are only 8 visible bands. We do not have any capability for thermal bands, or that would be necessary for SST.
Okay, thank you, Sean. And I did want to note that we have entered the extended Q&A and we will continue forward until 3:15. So the next question is, are the RRS data validated with in situ spectra? Once I looked at the data, if I'm not wrong, at the end, there are 4 RRS bands. Is this because some of them are removed because of noise?
No, so because the instrument has the ghosting issue, we're unable to use the 2 near IR bands for the atmospheric correction. We have only the 670 nanometer band, which would have been used for remote sensing reflectance, is now being used for atmospheric correction. So we do not, we can't do both. Our assumption there is that there's 0 modeling reflectance at that band if we're using it for atmospheric correction. But that leaves us with the 5 additional remote sensing reflectance bands in the blue and the green.
Okay, thank you, Sean. The next question is, how can you process HawkEye data from level 1A to level 1B to view all available bands? Can we do this in CDOS?
Yes, you can. In order to do that, the level 1A data are not geolocated, so there is a program that is provided with CDOS called Geolocate HawkEye. And that program is run first. It takes only a few seconds to run, but it will take that level 1A file and generate a geolocation file. If you have that geolocation file and the level 1A file, you can use L2Gen, the same program that's used to generate the derived products, to produce effectively a level 1B product, which will apply the calibration tables that are used during atmospheric correction processing to get the calibrated top of atmosphere reflectances or radiances as you desire. So yes, it's capable of being done within CDOS.
Thank you, Sean. Let's see, the next question is, if you cannot find the land coastline in the HawkEye image, what is the helpful information to work the manual navigation adjustment?
There isn't. So this is why we generally, if you notice, the imagery were for the most part collected near land, at least with some of the image covering some landmass of some kind. If we do not have that ground tie point to compare to, we are unable to make any adjustments to the onboard navigation, so it won't be as accurate.
Okay, I appreciate that response. We do have quite a few questions here. So again, if we don't get to your question prior to 3:15, we will have our speaker and panelists follow up with you offline. So the next question is, okay, is there a benefit in having a large number of these CubeSats to collect data on an operational basis?
There could be. We don't have that right now, but if you had more of these, you would be able to collect more than the limited, 18 scenes that we're able to capture in a day. You would, also have the benefit of, like, if one of the instruments failed, that there would be others that would be able to continue to collect data. So, yeah, since they are small, they're easily launched, and relatively low cost. If someone were able to fund more of these, it would I think be a benefit.
Okay, great. It looks like, I'm hoping I have not missed any questions in here. The next question is, does NASA have a plan to increase the resolution of the next ocean sensors?
The next big ocean sensor that NASA is working on is the ocean color instrument that will be on board the PACE platform, the phytoplankton. Oh goodness, here I am losing my head. Anyway, PACE. That instrument is going to be global in scope, but also hyperspectral. And the trade-off of going hyperspectral and global meant that going higher resolution spatially was going to be difficult, if not impossible. And so the instrument will be nominally 1 kilometer resolution.
Okay, thank you, Sean. And I was going to actually add the PACE mission URL to the Q&A here. Let's see, it's pace.gsfc.nasa.gov, and I will also add that to the chat. I'm just scanning the Q&A here. I don't see any additional questions. Let me make sure I have not missed any. Then I'll check back in the chat because we may have some there.
Jennifer, while you're doing that, I'd like to add to Sean's comment. So I want to mention here that the SeaHawk CubeSat mission was actually led by a public university in the United States, and that's the University of North Carolina, Wilmington. And then they partnered with NASA and some private industry partners to come up with this SeaHawk mission. So it's not technically a NASA mission, but we're so lucky to have had all this help from NASA. And in essence, it works like any other NASA Ocean Color mission. And I also wanted to mention that the PI of the mission, John Morrison, added in the Q&A some comments about the actual cost of the CubeSat. And I think that's also important to mention because some people were asking about that. The actual cost of construction and testing of the satellite was on the order of $500,000, and the launch costed $250,000 at the time. That was 3 years ago. And one of the exciting things about CubeSat technology is that it's growing so fast. There's so many people now interested in this technology that there's more shared ride missions or rideshare missions, and the cost of launching is also dropping. So when we were thinking about launching the second CubeSat, SeaHawk 2, the prices that we were quoted for launching were half of that, were 125,000. So I just want to clarify this because we as a mission are very excited about what has been accomplished with at a very low cost, and we're excited about what the future could bring if we could have a constellation of these CubeSats together with a big mission like PACE, or we could continue to improve the technology of the technology that SeaHawk spearheaded in terms of ocean color. Oh, actually, we have Hassel online. He can also, he was an engineer, and he can respond to more exciting questions about this. Thank you.
Well, thank you so much. I appreciate it. And the response that just came in through the Q&A gets to the question regarding when was it launched? Was it launched close to a solar minimum? And Hessel has indicated that yes, it was launched close to a solar minimum, although deorbiting timeline also depends on a satellite cross-section. There was actually a question posed in the chat pretty early on, and that was, how do you account for the glint? And I did miss that, so my apologies for that particular participant.
Oh, well, the SeaHawk spacecraft does provide us the ability to point. And so what we do is we effectively angle the look so that we're looking down at approximately 20 degrees, which is similar to the tilt that the CWIS instrument and the upcoming PACE instrument will have, which is a way of mitigating the impact of glint. We look away from it.
Thank you, Sean. And there is another question in the chat that I'd like for us to address, and that is, how is radiometric calibration performed and checked in flight?
In flight, it's not radiometrically calibrated. What we do is there was an instrument calibration that was performed pre-launch, and what we do on orbit is that we apply our vicarious calibration techniques that we use for all of our ocean color sensors to provide to adjust the on-orbit gains with vicarious gains to bring those radiances into better agreement with truth.
Okay, thank you, Sean. I am just checking to see if there are any additional questions. I don't see any additional questions, and so as a reminder, what I will do, we've only got a couple of minutes. Okay. There is actually a question. Give me just one moment here. Okay, so the question just came in. Okay, you mentioned that there were private investors in the mission. Do you foresee or do you think this type of mission could be commercially viable? Have you assessed if there are users willing to pay for these data? There's really kind of a couple questions in here. So the first part, do you think this type of mission could be commercially viable? And the second piece, have you assessed if there are users willing to pay for these data?
Well, I don't know that I can respond to that as a, my goal in life and my job in life is to give our data out for free. So I don't know about commercial viability of it. Yeah, or if anyone would be willing to pay for something that I'm giving you for free. So if Sarah has any thoughts on that, maybe she can chime in, but I'm
Thank you, Sean. I personally have not looked into it. It's a great question. As a scientist, I don't usually think about these things, but it is a great question. As Sean mentioned, and well, the whole purpose of this was to make it freely available for everybody. So we never looked at the commercial impact of this. There are commercial ocean color CubeSats, or no, I shouldn't say ocean color, but there's commercial CubeSat companies that are operating and delivering the similar imagery, but not a dedicated mission for ocean color per se. I'm not so sure whether they'd be interested or if there'd be enough people willing to pay for this, but it is something to explore.
Okay, thank you, Sarah. I am not seeing additional questions, and we have reached the end of our extended Q&A period. So at this point, what we will do is we'll log off from the audio component. I will leave the virtual meeting space opened. The polling questions have also now closed, but certainly if you think of something, you have any questions, please feel free to post those questions in the chat or the Q&A. So we'll leave the meeting space open an additional 10 minutes. I'd like to thank all of our panelists and also additional members of the SeaHawk HawkEye team that were able to contribute and participate this afternoon. We really appreciate it. And then a giant thank you to all of our participants for joining us this afternoon and to our speaker, Sean. So with that, I just wanted to remind everybody that I will be sending the recording link along with a link to this afternoon's presentation slide deck out to all registrants. So if you know of a colleague who registered but was unable to attend, and for all of you, you'll be able to take a look at this in the next week to come. It should take me just a couple of days. All right, everybody, our next webinar will be taking place on February 23rd, and we'll focus on synthetic aperture radar data. And we should have an announcement up on earthdata.nasa.gov in the next week or two. All right, well, with that, let's log off from the audio component. Thanks to all of you, and I will leave the virtual meeting space open. Okay, thanks so much, everybody. We appreciate it. Have a good afternoon or evening. Okay, goodbye, everybody.